In this video, we're going to discuss multiple regression. There is one caveat that I want to go ahead and tell you guys. For our course, we're only going to look at quantitative predictors, so numerical predictors. In your next statistics course, you expand this analysis to include both categorical and quantitative predictors. Let's talk about the general multiple regression equation, right? So while simple linear regression uses just one predictor, one independent variable to predict your outcome variable, multiple linear regressions uses any number of predictors to predict the outcome variable. And so our equation can be different sizes. And so I just have a general multiple regression equation here. It looks very similar to the equation that we saw when we had simple linear regression. It's just that we have more terms with more variables x, right? So I have my predicted y, our outcome variable, equals a plus bx. Well, since we have more than one x term, I can call it b sub 1 times x sub 1 plus slope times another predictor variable plus the slope times another predictor variable. And we'll continue adding terms until we get to the end of the list of predictors that we have. And so I'll go to the slope times the last predictor with a subscript k, where k represents the number of predictors we have. All right. So it has the same form. It looks a lot more complicated, but it's just an extension of our simple linear regression formula. A is still the y-intercept. The only difference here is that it's the value of y when all of the x's equal 0. All right? It's the value of y when all of the x's equal 0. Your slope has a very similar interpretation as well, but we have to accommodate or account for the differing x values. So there's multiple slopes here, right? So a slope b sub I is the slope of the variable x sub I. It is the amount that y changes when that x sub I changes by 1 unit or increases by 1 unit while holding all of the other x's constant. So we're just seeing how much that x variable changes y, ignoring all of the other x sub i's. So that's what with all other x of i's held constant represents. We want to know the effect of this x on y, so we have to hold all of the others constant. When we dealt with simple linear regression, we did not, and actually when we looked at correlation, we did not explore any assumptions. And the truth of the matter is we'll probably more often look at multiple linear regression rather than looking at correlation and simple linear regression. And so this is where I'm going to start talking about assumptions. Now, this is just an introduction to assumptions. There is more to these assumptions than I'm going to go over here. So please make a note of that. There's more to these assumptions, more diagnostics that we can do to ensure that our data should validly be used on, or our results are valid based off of the data that we have. I am going to list all of the assumptions. I'm just not going to list all of the ways that we can check these assumptions. All right. So one of the assumptions is that we have linearity, right? With simple linear regression, with multiple linear regression, there has to be a linear relationship between your predictors and your outcomes. One way to check this assumption is to check a plot of the residuals versus the predicted values. All right. That plot should show random scatter. This is one of those times where I want to see everything looking completely random, almost when we had a weak correlation. All right. And so this graph that I see here is an example of random scatter that would support this linearity assumption being satisfied. All right. I don't want to see any patterns in this plot of the residuals on our y-axis and the predicted or fitted values on our x-axis. If there are some relationships, um, then we might be missing some important variables, or there may be some relationships that we are kind of ignoring in our analysis. So linearity is one of the assumptions. Another assumption is the independence of errors. Remember, I said errors and residuals are synonyms of one another. So residuals should be independent of each other. Is the same way of saying independence of errors. Um, I'm also going to check this same plot here and ensure that there are no patterns or clusters in that residual plot in order to satisfy this assumption. So this graph here supports that both of these assumptions are actually satisfied. The third assumption is homoscedasticity. We talked about that when we talked about the homogeneity of variance assumption with ANOVA. This is homoscedasticity is the term that we use in regression. It just means that our residuals should have constant variance at all levels of the predicted values. So that means I need to see consistent spread in that residuals plot. Well, if I have completely random scatter across this scatter plot of the residuals versus the fitted values, I have also satisfied this homoscedasticity assumption. So this one plot is going to satisfy, or we're going to use this one plot to test all three of these assumptions here. Now, this is a good example of a plot that satisfies these assumptions. Violations of that assumption would look something like one of these scenarios here. We may have a fan shape in our graph. Some people say a fan or a funnel shape that looks like this. Notice it's kind of a pattern in this data set. It starts out with our variance in our residuals being very thin, and then as I continue to go out, the spread of our residuals vertically gets wider and wider. That definitely violates that homoscedasticity assumption there. All right. Another example is the pattern that I see in this residuals versus predicted values plot. There's some relationship going on between these residuals, right? Given these fitted values. So that may be evidence that that linearity or that independence or that homoscedasticity assumption is violated, right? And then I have another example that sort of looks random at first, but notice here I have differing values. That homoscedasticity assumption is definitely failed here. If I have any of these, I'm just going to say that at least one of these assumptions are violated. I'm not going to specify which one. I'm just going to say I see a pattern in my residuals versus my fitted values. That's evidence that some of my assumptions for my regression analysis is not satisfied. However, if I see random scatter without any patterns, I know that all three of these are fully satisfied. All right. There are some other assumptions. They don't use those scatter plots, the residuals versus the fitted values or the predicted values. The fourth is the normality assumption. Remember, we're using, you'll see that we're using f-test. We're going to be using t-test and things of that nature, and those require the normality assumption. So we want our residuals to be normally distributed, all right? We're going to use the QQ plot. They should show that the points are close to that line. So an example of satisfying that assumption is something like this. Notice we may have some veering off, right? Like this point, this single point out of all of these other points this point is relatively far off from the line in comparison to all of the other points. But this is still evidence that we have satisfied this normality assumption, all right? An example of not satisfying this normality assumption is seeing a particularly skewed, um, well, this is a graph that of data that's going to be skewed, but seeing a curved picture or scatter in our scatter plot, a curved pattern in our scatter plot will be evidence that we have violated that normality of residuals assumption. And then the last assumption is specific to multiple linear regression. It has to do with multicollinearity. Multicollinearity occurs when there are some of the predictors that we're using in our multiple regression model, they're correlated. They're probably significantly correlated. We don't want that to happen because it'll inflate the variances, which is going to mess up our hypothesis test and any confidence intervals that we want to draw conclusions about. All right, it inflates the variances, and we don't want that because we're going to get less powerful tests. And so, what we're going to do to check to see whether this assumption of no multicollinearity exists or if that assumption is violated or not, we're going to calculate what we call the variance inflation factor. Remember, I said that when you have multicollinearity, the variances are going to be inflated. That is bad. We're adding more noise to our analysis, which prevents us to finding or detecting an effect, or finding or detecting something significant. And so we want to calculate that variance inflation factor, which we abbreviate with VIF. If that VIF is less than 10, then we have no evidence of multicollinearity, and that assumption is satisfied. However, we will violate that assumption if we see a VIF that's greater than 10. I'll show you how to get all of those plots and the VIF in an example shortly. Now, we're going to talk about methods for building models. Sometimes these multiple linear regression equations are known as models because we're modeling or fitting the data. One of the methods for building or creating a multiple linear regression equation is to use stepwise regression. Stepwise regression starts with no predictor in the model or in the equation, and it step by step adds predictors one at a time based off of significance, right? So it'll try adding a predictor to a null model or a model that doesn't have any predictors. And if the p-value is less than or equal to 5% or alpha 0.05, then we'll keep the variable in that model. But if that p-value is greater than that 5%, greater than the 0.5, we'll remove it and then try to add another predictor. And we'll continue this process until till there are no more predictors to add based off of significance. That is called stepwise regression. Another method, which is the method that we're going to use, is known as backward elimination. With backward elimination, we start with all of the predictors that we think could be significant predictors of our outcome variable. We start with all of them in the model, and then we'll remove them one by one based off of the predictor with the largest p-value that's not significant. And remember, not significant is greater than 5%, which is our alpha. And we're going to continue this process, continue eliminating until we end up with only significant predictors in our model. All right, we're going to use backward elimination. Before we look at an example, I want to tell you about some things to remember in JASP. Well, this first thing to remember is that for us, we're not going to use non-quantitative predictors. We're not going to use non-quantitative predictors. So categorical predictors require a little more thought, and that's going to be the topic of, I think this is the second topic. You're going to revisit regression in your next statistics course, and you're going to talk about how do you add additional predictors, and then how do you test those assumptions more broadly compared to what I just went over in this course. So we're just giving an introduction to multiple regression for now. But in JASP, we already saw the linear regression menu. We're going to place our y variable, our criterion dependent variable, in the dependent variable box. We're going to select backward in the method, and we're going to place our predictors in the covariate box. It's going to be called covariance. With backward elimination, we're going to use an alpha of 0.05. The backward elimination method default in JASP is not 0.05, it's a different value. So we're going to have to change this p-value every time in the method specification section. And then to get everything we need for our assumptions, we're going to select tolerance and VIF in the statistics coefficient section. We're going to select residuals versus predicted in the plots, residual plot section. And then we're going to do the QQ plot standardized residuals in the plots, residual plots section. All right. And so let's look at our first example, and we'll go through a full analysis with this example here. It says a community development social worker is investigating factors that may significantly predict heating costs. A random sample of 20 homes was selected, and data were collected on the following variables. We have the mean outside temperature, which is in degrees Fahrenheit, number of inches of insulation in the attic, age of the furnace in years, and then the heating cost in January. The goal is to determine which of these factors significantly predict heating cost at the 5% significance level. Well, first, we need to know which variables are our predictors and then which variable is our predicted, right? Well, of course, we have mean outside temperature. If I go to JASP, I'm going to open JASP right quick. And I put this data in a different data set just so that that data from correlation and regression, which is also in this module, the data set wouldn't have so many variables. So we're going to go over two examples. And in this example, we have cost, temp, that's the mean temperature outside. This insole is the insulation. That is the number of inches of insulation in the attic. And then we have age, that's the age of the furnace in years. Now, in this data set, we do have a categorical predictor that is an indicator variable as to whether a house has a garage or not. This is a factor, but we're not going to actually use this variable. We're only going to use these three. So these are our predictors. These are our independent variables. So they're going to go in that covariance box. And this cost, this is the monthly cost of your heating bill based off of what we have in our data set. So when it says what are the independent variables, the temperature, insulation, and the age. And the heating cost is our dependent or predicted. All right, what we're going to do is we're going to run the model using backward elimination, and then we're going to obtain model diagnostics. So when we're assessing the model assumptions, the linearity, independence of errors, homoscedasticity, normality of residuals, and no multicollinearity, we're going to run, that's the same as running model diagnostics. So sometimes if you go online to help you study, you'll see people say, oh, what are the model diagnostics for this regression model? It's the same thing as assessing those assumptions. So we're going to determine if the data satisfy our model assumptions. Let's go to JASP and see how we can do that. So I already have my data here. I'm going to start in this regression module here, and I'm going to go to linear regression. I like to see the full screen when I'm on this screen here. We said that cost is our dependent variable, so I put it there. Our method is backward elimination, and then temperature, insulation, and age are the variables that we're going to try to see whether we get which of these are significant. We'll get to that later. What I'm going to do is I'm going to ensure, one, that in this method specification section, I change this removal to 0.05. so that I'm going to remove any p-values in this backward elimination method, any p-values that are larger than 0.05. All right. So that sets my model together. All right. Before we get to analyzing the results of the model, I want some plots and some statistics. Right. So under the statistics section, I want to add tolerance and VIF. That is something that I want. In the plots area, I want the residuals versus the predicted. So I'm going to check that. And I want the QQ plot of standardized residuals. I'm going to check that. These are my two plots. This plot here of the residual versus predicted assesses independence of error, linearity, and homoscedasticity. This QQ plot here assesses the normality of residuals. And then my tolerance and VIF are in this section here. Now, before I get to interpreting all of that, these are the outputs of my regression model, all right? In this model summary, my output variable was cost, so it has the outcome variable or predicted. This kind of gives us a hint as to how many models did we run. The first model is always on this first line. And remember, I said that backward elimination always starts with a model that contains all of your predictors. So this M with a subscript 0 is a model that has all three predictors: temp, insulation, and age. This second model is the model after we remove one of those variables, right? The least significant variable. You can't see all of that information here, but if you skip to the coefficients table, you will be able to see all of that information. So for instance, that first model, which is M sub 0, is here. It has an intercept, which we have A. My B1 will be the slope for temperature, is on this line. B sub 2 will be insulation. B sub 3, slope for age. All of that information is given here. My second model, and notice here, the difference between my first model and my second model is that age has been removed. Well, if I look over here to the p-value for age, its p-value is insignificant. It's greater than 0.05. So that means backward elimination removed that p-value and then reran another model. And this was the last model that I have because I only have evidence that it ran two models here. So this is my final model. And so when I look at my VIF, I'm going to be looking at these two values here because it's the values for my final model. All right. So let's evaluate all of that information for our example here. So, well, to test linearity, independence of errors, and homoscedasticity, I want to look to see that I have random scatter and not any patterns in this data, in this scatter plot here. And that is the case here. And so I can say, since they have the random scatter supports that all three assumptions here are satisfied. I don't see any patterns. I don't see any fanning. I don't see any trends or anything like that. This is good evidence that we have satisfied all three of those assumptions. Now I'm going to move to my normality of residuals. I want the points to be close to the line, even if one or a couple are not close. As long as I don't have a noticeable curve away from that line, I have evidence that we satisfy the normality of residuals. This is the case here. Most of these points are close to the line. This assumption is satisfied. Now, when I look at my model, I'm going to look at that last model there. As long as my VIF statistics are less than 10, I have satisfied that I have no multicollinearity. So I can believe the results of any F test or especially the hypothesis test for my coefficients. So since both VIF values are less than 10, I know that I have no evidence of multicollinearity. So all of my assumptions in this example have been satisfied. So now I'm going to go table by table to show you what information we get from that table. So I showed you that model summary table. Our cost variable, once again, is our predicted variable. That is here. In this table, we have the R value, the R squared value, and then an adjusted R squared value that we're going to talk about here for each of the models. Remember, I'm going to focus on that final model, so I always look at the last line in this output here. Now, we could look at the R squared to see the proportion of variance in the predicted that's explained by our significant variables in our model. But that coefficient of determination has issues. It actually increases or gets bigger as we add more and more predictors. That is why you see for model M sub 0 that the R squared value is larger than it is for M sub 1, our model with just two predictors. All right, if I continue to add more, this value is going to get higher and higher because you add more data to possibly explain, you're going to explain more variance. And so the adjusted R squared actually accounts for the number of predictors that are added in the model so that you won't get an inflated value. You'll usually get a more accurate value for the proportion of variance that is explained by the predictors. And so what we're going to do is when we use multiple regression, we're going to use the adjusted R squared when we're providing the percentage or the proportion of variance in that predicted variable that is explained by the predictors in that final model. And so here our value in our final model is 7.721. So we can say about 72.1% of the variance in that outcome variable, which is the heating cost, is explained by the two variables in that final model, insulation and temperature. That is our model summary table. Now let's go to our ANOVA table. So that is an error there. Sorry. That's our ANOVA table. And if you go back to JAS, it's the second table here. Now, for each model that we run, we're going to get an ANOVA table. Oh, Dr. Pompey, why do we have anything about ANOVA here? Well, what is happening is we're doing a global F test to assess the overall model fit. So is the model itself explaining enough of the variance in that predicted variable, right? That is what this ANOVA F test is doing. It indicates whether the overall regression model is statistically significant, which is basically saying, does the set of predictors explain a significant proportion of variance in Y? And so as we can see, for each model that it runs, it is going to run a regression model. It is using ANOVA. Remember when we did ANOVA before, we had the between group here, variable here, then we had the residuals. And we said that if we did the sum of squares divided by the degrees of freedom, we get to the mean squares for the between groups and the within groups, which is the residuals. And then if we do the ratio of the mean squares, we get to that F statistic with these degrees of freedom in the numerator and the denominator. The same exact thing is happening, but now we're doing the mean squares regression versus the residual. So is the regression explaining enough of the variance to say that this model is significant or not? So this is so good. But instead of saying between groups, now we're saying regression here, right? And that'll provide evidence that we have a significant model. Well, when we interpret this, we want to go to our final model. So I'm going to go to the model closest to the bottom here. So in this case, we only ran two models. So it's my second model, M sub 1. And this F statistic, 22.005, with the degrees of freedom in the numerator of 2 and the denominator of 17, led to a significant p-value. This is less than 0.05. And so our interpretation is that since we have this F statistic, F statistic with this significant p-value, the model is statistically significant. This indicates that at least one predictor contributed significantly to explaining heating cost. All right. So we have a significant model basically. So I can go further and interpret the results for specific variables. Now we're going to go to the last table, and that last table was in our coefficients, was our coefficients table. I go to that bottom model coefficients. Coefficients in that bottom model, sorry. All right. And so we have an unstandardized column here, which gives us our coefficients for our regression equation, if we wanted to write our regression equation. We have some standardized coefficients for our slopes. We're going to talk about that in just a second. This standard error is used to help us get the test statistics from our students' t distribution, and that helps us get our t values. All right. So if I'm going to interpret these coefficients, we already went over this. The final model ended up with two significant predictors, insulation and temp, and that was done after two iterations. Notice, if either of insulation and temperature were not significant here, meaning these p-values were greater than 0.05, then we would go another iteration and we would see another model. But since both of these were significant here, this model stopped here at m sub 1. Now, before we write the equation and actually interpret the regression coefficients, I want to differentiate between the unstandardized and the standardized regression coefficients. Unstandardized coefficients represent the results in the original units of each variable, right? So they represent the amount by which our dependent variable y changes when the predictor variable x, that specific predictor variable x, increases by 1 while holding all of the other predictors constant. So this is primarily used for interpreting the effect of the predictors in their original units. All right. Sometimes it can be a little misleading, especially if the units are wildly different. So, for instance, if I had a model, and it's not with this model here, but if I had a model with the variable age and income as a predictor, and because income has a wide range of values, like it could be in the thousands and hundreds of thousands, and even in the millions, the regression coefficient might be slightly it's harder to see whether one predictor is having more of an effect on the predicted value or in the model compared to the others when the units are wildly different. Trying to do that example in my head it's probably not going to be clear to you, even if I could explain it very well. And so we're going to see an example where sometimes we don't want to use the unstandardized coefficients to see which predictor actually has more of an effect on the outcome variable in a model. When we want to see that, we use standardized coefficients. Standardized coefficients are sometimes called beta weights. These are the coefficients, or the slopes are in this case going to be expressed in standard deviation units. They indicate the number of standard deviations the dependent variable y is expected to change for a one standard deviation change in or increase in the specific x value while holding all of the other indicators or predictors constant. So by standardizing these and putting them in standard deviation units, we can make a comparison across the different regression coefficients so that we can know which regression coefficient has more of an impact on our outcomes in our regression model. So it says it's useful for comparing the relative importance of predictors measured on different scales. All right. And so what we're going to do in this example is we're going to look at that last model and we're going to write the multiple regression equation based off of the output. And then we're also going to see which of the significant predictors are more important to this model. Of course, they're both significant, but the level of significance can be determined by the standardized regression coefficient. All right, for this model, I know that my intercept is 490.286. My unstandardized coefficient for the insulation variable is negative 14.718. And the unstandardized regression coefficient for temperature is negative 5.15. And so I can put that together in my regression equation. Remember, your heating cost in January was your outcome variable or your predicted variable. I have my intercept. You can say plus negative or you can just say minus. But I have minus 14.718 times the insulation variable, minus 5.15 times the temperature variable. This is my regression equation. Both of those are significant. So I know insulation and temperature are significant predictors of heating cost, while the age of the furnace is not. In this, when I look at my standardized regression coefficient, if I look at that in absolute value, the standardized coefficient for temperature actually has the largest value if I ignore the negative sign. That indicates that temperature has more of an effect on heating cost compared to insulation, right? Now, if you were to just look at the unstandardized coefficient here, just because this insulation has the larger in absolute value unstandardized coefficient, it may make you think that insulation has more of an impact on heating costs. But that can be misleading because of the units of these variables as well as the units of heating costs. And so we use the standardized regression coefficient to get the level of importance of each of those significant predictors. Temperature is more significant or has more of an impact on heating cost compared to insulation. They're both significant, but temperature has more of an impact. Let's look at another example, and this time we'll kind of go a little quicker through the entire process. So it says a social researcher wants to examine how family income, family size, and the total years of education beyond high school for both parents predict the size of a home in square feet that a family chooses to live in. We're going to use backward elimination and a 0.05 significance level to determine which variables significantly predict the size of the home to be purchased, and we're going to write the final regression equation. All right, and so I'm going to get rid of this. I'm going to look at my same data set. This is a very small data set. And I'll say this, and you'll probably talk about this more in your next statistics course. The smaller the data set, the less likely we're going to want to use multiple regression. Multiple regression is a large sample size. Most of the statistical methods that we've dealt with are large sample size methods, right, which require a large sample size. And I know that we said that the central limit theorem ensures that, hey, if our sample size is greater than or equal to 30, then we can, assume that things are normally distributed. But we even need larger sample size so that we can more accurately conduct all of these tests. And so this data set, while it is small, it is just used for an example. We need much larger sample sizes here. All right, but let's move on with this example. We have the square footage of the home here. We have the income, the family income. We have the family size, so the number of people in that household. There's a variable called senior. This variable indicates it's a categorical variable that indicates whether there's a senior citizen living in the home. Since we're not doing non-quantitative variables, we're not going to use this in our model. And so that, but it is in the data set. And then our last variable that we are going to use is the education. It's the number of years of education beyond high school for the parents. And so if I want to run this regression model, I'm going to go to the regression module, go to linear regression. Square footage is what my outcome variable is. I'm going to use the backward method. Income, size, and education are my predictors. All right. Into my method specification, I'm going to adjust this to 0.05. 0.05. And notice here, I ran 3 iterations. Model 0 has all of my predictors. Model 1 has 2. And my final model is a simple linear regression model. Okay. All right. So I can look at this final model here. And the first question said use backward elimination and determine which variables significantly predict the size of the home. Only the family size was a significant predictor of the square footage of the home. Family size. That is the only significant predictor. Income was insignificant, as well as education. It was the family size. My final regression equation is going to have an intercept of 1271.586 and a slope on the family size variable of 540.690. All right, and so the answers to those 2 questions is family size is the only significant predictor of home square footage. The final regression equation is this regression equation here. It says using the results of your multiple regression, interpret the adjusted multiple coefficient of determination. That value is given in our results here under adjusted R squared of 0.802. And so we have 80.2% of the total variation in your house square footage is explained by the size of the family. All right, our last question here are the assumptions met? Well, for us to check the assumptions, we're going to go here to statistics. Under statistics, under the coefficients section, we have tolerance. Oh, by the way, I didn't focus on this here, but if you wanted to get confidence intervals for in your final model for your regression coefficient, your slope, you can get that here. So we're, in this case for M2, that's our last model for the slope for the family size variable. Under the headings 95% confidence interval, we can say that we're 95% confident that the slope, so that's the effect of family size, will be between 337 and 744, right? And remember, your slope is a measure of the increase or decrease in y for a 1 unit increase in x, right? So if for each additional 1 person increase in family size, so if I increase my family by 1 unit, I expect in the population for the square footage to increase by between 337 and 744 square feet. That is the interpretation of that confidence interval. I didn't focus on the confidence intervals in this module, but they still exist and can be used and interpreted in a very similar way as the confidence intervals from before. But we're assessing the whether the assumptions are met. I'm getting the tolerance in VIF. You're going to learn about tolerance in your next statistics course. And then in the plots, I'm going to get the residuals versus the predicted. and the QQ plot of the standardized residuals. All right. So this is why the sample size being 10 is so bad. All right. For the most part, this shows random scatter, right? However, this one point is throwing everything off. All right. Now that can be a sampling variability issue. This point can be an error. This is throwing me off. It's making it seem like the variance, so homoscedasticity, is not being met here because for the values around 3,000 or a little less than 3,000, they have a wide range of residuals. The residuals here are not as equally spread as the residuals over here, as well as the residuals over here. This one point is kind of throwing this off. And also, there are not many points over here to really talk about the variability. This is why small sample sizes using these parametric statistical methods is kind of difficult to support, right? I'm going to say here that the assumptions of linearity, independence of errors, and homoscedasticity may not be met here. And this is because of this one point here, and maybe because of this area over here not having a point may not be an issue, um, more so than this single point here. So I'm going to say that the residual versus the predicted values plot shows random scatter except for one point. So I'm going to proceed with this regression, but I'm going to proceed with caution because those three assumptions may not be met. Again, it can be a product of the small sample size, or there can be other issues. But if I were in real life doing this research, I would explore this specific data point here, see if it's an error, see if it's what we would expect in the population, so on and so forth. How influential is this point to my results? I may remove this point from my data, run the analysis, and see if I get much differing results. Things of that nature. There are things that we can do to accommodate for that. You're going to learn all about that in your next statistics course. What I want you to do is just kind of see some of the methods that we can use to test these assumptions for now. So I'm going to proceed with caution. That residuals versus predicted plot makes me nervous. So the assumptions may not be met. The QQ plot of the residuals, this is a pretty good plot. You may say that this point right here may be a little far off from the line and it's getting to be a little curvy, but these points here are still close to the line. So most of the points are close to the line. This one may be related to this point here, which is throwing us off. So our normality of the residuals may not be met. To be honest, this is a good plot. This is not too far from this line. So I'm going to say my normality assumption is probably met. Now, you're probably saying, Dr. Pompey, I'm not comfortable with that. And so we could argue with that. That can be a very good argument that someone can make. Which is why using some of the statistical tests, I think before we use the Shapiro-Wilk test as another measure to add to determining whether we have normality in our data. But this is about the residuals, and so we don't have that assumptions plot for this example. And so you're going to see in your next statistics course some ways to get around that. But since these points are close to being on the line, even this point here, I'm going to say that the normality assumption is met. Okay, I need to see extreme curvature away from the line for me to doubt the normality assumption for us with this linear regression. All right. The final thing to look at is the variance inflation factor in our last model. Our variance inflation factor, this is less than 10, and so we have satisfied that there is no multicollinearity in our data. And so for me, for this model, the VIF is less than 10. No multicollinearity is satisfied. QQ plot shows points near the line. Normality of residuals is satisfied. The residual versus predicted shows random scatter except for one point. This point might be very impactful on my results. So further exploration into those model diagnostics is needed. So those interpreted results that we found in parts A and B, we should interpret those with caution. All right. And so, again, you're going to get to your next statistics course. You're going to start talking about statistical power. We did not talk about statistical power in this course, besides defining it when we talked about type 1 and type 2 errors. But remember, statistical power was the probability of rejecting a null hypothesis when it needed to be rejected, when it was false. And then you're going to get right back to revisiting multiple regression. You're going to talk about the assumptions in more detail. So we're kind of waving our hands on the assumptions now. You've got an introduction. You're going to add to that. And then you're also going to talk about how to handle categorical variables in your multiple regression models. That is all for this video. This completes all of the content for our course. And so make sure you get to do those practice problems. And as always, let me know if you have any issues or questions about anything. That is all for this video. I'll see you in your other assignments.